Hello, YouTube! Today we're going to be talking about Newton's second law. So far we've talked a little bit about how to figure out what forces are. And find out what your net force is by adding up all your forces. Today we'll be talking about the second way to figure out what your net force is and why that's actually useful. Let's dive in. In particular today, if you're able to use the equation from Newton's second law to describe motion, you're in great shape. Vaguely speaking, if you can explain Newton's second law, that's great, but honestly, it's literally just an equation, so if you're good with the equation, that's the more important part. In particular, if you can look at problems, figure out what your givens are, set up your free body diagram, get your net forces all sorted out, add those up like we were doing from before, and then set that equal to the thing from Newton's second law equation, you're in great shape. And that is basically what we'll be doing for a while. So there should be a couple days of practicing this. One thing that's a little bit weird about this, as of recording, I think I used primarily book problems for this as opposed to having a worksheet. I will probably translate some of those book problems into the worksheet at some point. But probably not when this video gets published. So if you are looking for practice sheets, I guess just hit me up in the comments and provide me with motivation to post that. Yeah. All right, so we've talked a little bit about mass. Here's it again. It's just about to be really relevant. Mass is how much matter is an object. That's not the same thing as how much space it takes up. It's how much stuff is crammed into the space it does take up. But mass is also a measurement of how much inertia an object has. Inertia is specifically how hard something is to accelerate, and the two can be used interchangeably. So if you hear someone saying the word inertia and you can't just substitute it in your head for mass, they are not using it right. Pretty much. In the same way that height is the measurement of the length of an object. So if you were talking about the length of a person, you're probably talking about their height. You're just using a weird way to describe it. And you could use the two pretty much interchangeably, even though they're technically a little different, because one is a specific subsection of another. Mass is a measurement of inertia. But it's the only measurement of inertia, so basically the same thing. So you actually probably already know Newton's second law. And to figure it out, you can just pretty much ask yourself, if you push something harder, should it accelerate more or less? Hopefully it makes some level of sense that if you push something harder, it'll accelerate more than if you push it less hard. So then, what if it's got more mass? If you try to push a car versus trying to push a bike? Well, the one with less mass should accelerate more, which means it's easier to accelerate something if it has less mass and harder to accelerate something if it has more mass. And that's really all that Newton's second law says. It just does it with math. So in words, and I will never make you know this, the acceleration of an object is directly proportional to the net force on the object and inversely proportional to the mass of the object, and the direction of acceleration matches the direction of the net force. Breaking that down, if you push something harder, it accelerates more. If it's got more mass, it's harder to make it accelerate, and then you can turn that into an equation. Before we do that and start doing some problems, I do want to talk about resistive forces. Do I not have a... So doing that, and this should have been in the slides but wasn't, what this is saying in words is that your acceleration will be equal to your net force divided by your mass, which I almost just wrote acceleration again. Typically, this gets written as net force equals mass times acceleration, where this is all one thing, meaning net force. The units on net force are newtons. This bit is mass, which is measured in kilograms. And this bit is acceleration. The yellow is a buffer between the red and the green, so sorry if you're red-green colorblind. Hopefully this isn't too bad. My handwriting, on the other hand, definitely quite bad. especially with a computer mouse. All right. So net force is equal to mass times acceleration. A is acceleration, m is mass. In particular, the thing that's a little weird about this equation is that sometimes the problem tells you the net force, sometimes the problem is asking you for the net force. Normally, however, what you're going to be doing for the strategies for this one is to find the net force the way that we were doing it previously, and then instead of saying, oh, that equals this number, you're going to say that equals the mass of the object times the acceleration of the object. And one other big thing that's important about this, it's directional. Meaning this will work for the y direction, this will work for the x direction separately, the same way that the net force can be found in the y direction and the net force can be found in the x direction. This will make hopefully more sense when we actually do examples. All right, so while we're doing problems, there's a third type of hidden force that I do want to talk about, which is resistive forces. Any force that's going the opposite direction as the way something's moving is called a resistive force. In particular, the two that we deal with in this class are going to be friction and air resistance for the most part. The book problems mention resistive forces, which is why I wanted to bring it up now. Pretty much it just means whichever way it's moving, make sure your force points the exact opposite direction. We'll get into more about what friction is and how to calculate it later, but for now, however big it needs to be to make the problem work, or it'll just tell you how big it is in the problem, that's how big it is. So, doing an example out, and again, hopefully this will clarify some of the stuff from before. So we have a 10 kilogram object that is, and this is unit 2.4 Newton second. We have a 10 kilogram object. So I'm going to have my object. It's 10 kilograms. And it's got a 40 Newton force going on it at an angle of 37 degrees above the horizontal. To the right. There is a 20 Newton resistive force on the object as it slides along the ground to the left. So the velocity of the object is like this. It's going to the left. And so that means that our resistive force, which I'm just going to call FR, is going to the right and will be 20 newtons. And this might look kind of weird. If it's getting pulled to the right, why is it moving to the left? And that's not really part of the problem, first off. But second, what this situation this is describing is one where the object is moving to the left because something earlier made it move to the left, and now there's someone pulling it to the right to make it slow down and stop. So just because the forces on it are going to the right doesn't mean it has to be moving to the right, and just because there's something pulling it to the right doesn't mean that the resistive forces will go to the left. The resistive forces don't resist pulling, they resist motion, which is velocity, not force. So just be careful on that. A is asking us to find the net force on the object. B is asking us to find the acceleration. And C is asking us to find the normal force. So in particular for this one, same as always, honestly, free body diagram. Draw our dot, great. Draw our force of gravity going down. Draw our normal force going up because it's touching a table. Draw our 40 Newton force that's in the problem already. And I'm going to call that one F1 again because I am not particularly creative. And I'm going to draw an arrow for our resistive force, which I know is going to the right and has a size of 20 newtons. Breaking stuff up into components, we know that we've got our force 1 in the x direction, which will equal 40 times the cosine of 37. And we've got our y component. So F1y, which will be 40 times the sine of 37. Yeah. I should throw that in a calculator. Although I know from experience that this one is 32 and this one is 24. So I'm going to save a little bit of time, and that one's 32, that one's 24. But shortcuts make long delays, so let's prove it. 40 times the sine of 37 is, great, 24 point very small, and 40 times the cosine is 32 once you round. All right, awesome. Okay, so from here, our next step is to find our net force just like we did before. But we're going to have to set that equal to MA if we can't just find the number. Now in our y direction, because this thing is sliding along the table, wrong color, in our y direction, we actually know that the net force has to be equal to 0. And that's because it doesn't start moving up, it doesn't start moving down. So it's in the y direction, remaining at a constant velocity of 0 in the y direction, meaning it's not moving that way. So I can go ahead and say that the net force in the y direction is 0. The x direction is going to be a little more complicated. In the x direction, my net force is going to be the sum of all my forces in the x direction. Well, I've got that 32 Newton force from F1x going to the right, and I've got that resistive force going to the right as well. And that'll be my net force in the x direction. In this case, we've got 32 newtons going to the right, and we've also got that 20 newtons going to the right. And so that'll give us a net force of 52 newtons to the right. As a reminder, if one of them is going to the left, you would make it negative, and they would probably wind up fighting against each other, but that won't be the case for this one. And that's it. Great. B. B is asking us to find our acceleration. Well, if our net force in the y direction is equal to mass times acceleration in the y direction, but that's equal to 0, and that just means that our acceleration is 0. So in the y direction, it's not accelerating. The x direction is where it gets a little more interesting. So in the x direction, and I'm going to set this up as though I hadn't already done it, just so you could see what it's normally going to look like. I know that my net force is plus F1x plus Fr. But my net force also needs to equal mass times the acceleration in the x direction. This is what you're going to do for basically every problem. Set up an equation, list out all your forces, have the ones in the x directions add up to ma, have the ones in the y direction add up to ma. Every time. So we have to do a little bit of math to solve for the acceleration. Divide each side by the mass, divide each side by the mass, and we're done. So our acceleration in the x direction is equal to F1x plus Fr over m. And that'll be 32 plus 20 divided by, I don't remember, 10. Which gives us 5.2 meters per second squared, positive direction, as our acceleration. Yeah. And that's it. Then we just have to do part C. I'm going to have to flip the page back and forth a couple times. Oops. So part C is asking us to find our normal force. Well, our normal force goes in the y direction. So now we're actually going to have to really look at the y direction and what's going on, because again, that's just the direction of the thing we're being asked about. So our net force in the y direction, we know needs to be 0. But our net force in the y direction also needs to be all our forces in the y direction added up all together. I seem to remember that there's normal force, I remember that there's F1y, and I remember that there's mg. Let's double check the directions on all of those. Normal force is going up, so that one will be positive. F1y is going up, so that one will be positive as well. mg is going down, so that one will be negative. Positive, positive, negative. And that all needs to equal 0. I need to solve for Fn, so I'm going to have to get rid of F1y and get rid of mg. Get rid of F1y, get rid of mg. And that'll leave me with my normal force is equal to mg minus F1y. M is 10, G is always 10, F1y was, I think, 24, but let's double check. Great, 24, and just double checking again, mass is 10. So minus 24, which is 100 minus 24, so 76. So our normal force for this one is 76 newtons going up. Great. So those are some examples of questions you can expect to see. Things can get a little more complicated. Things can get a little less complicated. Thanks for watching, and goodbye, YouTube.